Okay. How do we compute eigenvectors, eigenvalues? We are at a point where we want to understand what are the eigenvalues and eigenvectors of a matrix, because from an intuitive point of view, whenever we have x dot is equal to ax, and we know that v is equal to lambda v, we got the intuition that this information tells us a lot about the dynamics of the system. Because, for example, if I have lambda 1 equals to 0, lambda 2 smaller than 0, we can determine that the origin, 0, is which type of equilibrium? Go, discuss. I heard marginally stable. Why? Because if this one is associated to this eigenspace, starting here as an initial condition leads to staying there. Starting here instead will indicate going towards the origin or going somehow towards the kernel, or you do not know. And this is for this specific case. Discuss. I have lambda 1 equal to 0 that is associated to this kernel. Okay, so if I start here, I stay there. And then I've got a negative eigenvalue. That means that if I start here, I will move. Because it's not an equilibrium, because it's not in the kernel. Together? Are we together on this? Perfect. It will move where? Will it explode? No. This indicates stability, true. Okay, if it indicates stability, it means that it goes towards the origin. That means also from here it goes towards the origin, or the movement is a different one. One towards the origin, different one towards the kernel, or you do not know. Discuss. Okay, people, what would you answer? 1, 2, or 3? I see several 2s. I do not see all 2s. The 2 is the correct one. Do you remember? So, in a certain sense, once we have the kernel, it means that all the points that are kind of starting from here plus the kernel. Some problem with the monitor. Okay, now you got it. Okay, this is the kernel. This is the point before plus the kernel. True? In a certain sense, all the trajectories starting from here will kind of lead to something that is parallel. True? Okay. If this thing here is not clear, the previous section, I think the previous modules that we were doing, they describe this in very details with some numerical examples. If this one is not clear, please, people, for tomorrow, go back and recheck, okay? Together? Those movements along the to be clear, okay? Why it has not? Imagine this situation here, and I give you kind of a counter example why it cannot be 1. If I have kernel, and I have this movement like this, and this movement like this, you see that in a certain sense, those ones are movements that are equilibria, so no movements. If this is the origin, you see that in a certain sense, it looks like that there's not one other eigenspace. Looks like that there's a lot of different eigenspaces. By tomorrow, for tomorrow, if it is not clear, you recheck, and in case it's still not clear, you ask. Okay? Perfect. So computing eigenvectors, eigenvalues pairs is very important because they give us the intuitions about how the system evolved. Okay? So we need to be able to characterize. Let's go. So, procedure. We take a vector that is different from 0. Why? Because if we take v equals to 0 and we do av, we get 0 independently of anything. So we need to start with v different from 0. Then, given at any v different from 0, we are asking ourselves if av is going to be equal to lambda v. Lambda in general also complex. Okay? If we get this situation here, is this one a good candidate for finding an eigenvalue? Definitely not. Together, how much are we following me, people? Very much? Not at all. Okay? What are we asking whenever we're asking this one? Whenever we ask ourselves this question here, we are asking ourselves this question here. True? This is actually the question that we are asking ourselves. We are asking if AV minus lambda V is equal to 0. That means A minus lambda I, V is equal to 0. True? Or vice versa, it's minus here plus here is the same. Okay? That means that we need to check whether this happens, whether the kernel of this modified matrix is non-trivial. True? And somehow we are checking these actually, because this means this. That means that there will be a V that satisfies this. That means that there will be a V that satisfies this for that specific lambda. And notice that here I can put a lambda or another lambda and verify whether this is happening or not. Let me make an example. A equals to 1, 0, 0, 2. Okay? And now I plug in here inside lambda equals to 0.5. What am I asking myself? I'm asking myself whether 0.5, 0, 0, 1.5, true? Here I'm putting lambda equals to 0.5, minus and minus, sorry. If the determinant of this stuff here is equal to 0. This, whenever I put this one inside here, I'm asking myself this question here. Are you following me, people? The answer to this question here is false. True? But if I put lambda equals to 1, what do I get? I get this one. And the answer becomes true. You see that in a certain sense, this one is a question. We are asking ourselves, for which lambda does it happen that determinant is equal to 0? Because for the lambda that this happens, it means that this happens. That means that I'm able to find V in the kernel. That means I'm able to find for that specific lambda that satisfies this one, a V that satisfies the eigenvector eigenvalue pair. Are we together, people? Let's do it graphically. So eventually, we are solving this polynomial here, true? We are putting S as a variable, and we try to find the S variables that satisfy this polynomial. We are trying to find the roots of that characteristic polynomial. Okay? Now, this is a graphical representation that works only for eigenvalues that are real. Okay? Are we together? Look at me. This graphical stuff that we are doing is only valid for real eigenvalues. But it's kind of interesting. This is the matrix that we are trying to investigate. True? What does it mean, considering this matrix here? It means considering this matrix here. True? What does it mean? It means that lambda is a variable, and I can change lambda. Let's change lambda real. It means that if I take A1, I am taking A1, that is this one, and trying to move with lambda this A1 along here. Do you see it? If I put Let's put with a minus that you see it's going to be a little bit easier to see. A plus here. If I take lambda equals to 1, it means that I'm modifying A1 so that it goes here. You see it? Do you see it? And if I put lambda equals to -1, I'm putting A1 that it becomes this one. Are we together, people? 1, 2, 3. When is it that the determinant of this one is going to be equal to 0? I am actually changing with lambda. A1, make it move along here. A2, make it move along here. Do you see it? Do you see that I'm changing the second coordinate? And I'm trying to find the lambda such that they modified, it's kind of rotating them, they become kind of similar. You see? Whenever I find that lambda for which I have A1 modified and A2 modified, do you see it? Do you see that I get a specific lambda for which I get that stuff there? There, it's when I have the determinant of this object here equal to 0. That means this, that means this is valid. Okay? Together? Think at this mechanism, find from a graphical perspective the second eigenvalue. The first one, lambda equals to 1.5, I think it should be 1.5. We found it, true? Because it makes like this and this, true? There's another lambda that gives me determinant equal to 0. Go, graphically find it. You see? We need to have the two modified columns to be aligned. A1 travels horizontally, A2 travels vertically. A1, the bigger I do this one, the more A1 goes in this direction, the more A2 goes in this direction. True? Do you see it? Modified A1, modified A2. I think it's maybe a little bit more, kind of like this, but you get it. True? Modified A1, modified A2. It's around 3.5. You see it? How much are we together, people? 1, 2, 3. I see some twos. Are there questions? Don't be shy, people. I know that those graphical representations here are kind of, probably you never saw this, true? How many of you saw this stuff? Question. So I move this one here, and I move this one here. I kind of get them aligned, true? And this means moving A1 of 1 point something, A2 of 1 point something. Approximately 1.5. It's not 1.5, 1.4 something. From a numerical perspective, we should be kind of computing stuff. But it's for sure not 2, and it's for sure not 1. It's around 1 and 2. So close to 1.5. Do you see it? And this one, I go down of 3 and something, and here I go left of 3 and something. True? How much do you see it? 1, 2, 3. This is valid only for real numbers. For complex numbers, it's 4-dimensional. We do not see the stuff. But in a certain sense, this should consolidate the intuition that what we are trying to find is modifying A through modifying coordinates so that we get determinant equal to 0. Perfect. And this is the generic way that probably you saw up to now in the algebra courses. Read it, tell me if we are together. Okay. Perfect. Examples, they are very, very, very trivial examples. Let's do not waste time. Interesting thingy. interesting thing. You know that whenever we have an upper triangular matrix, the characteristic polynomial is going to be what? It's going to be essentially the product of S minus the stuff on the diagonal. The characteristic polynomial tells us the lambdas. True? Tells us the lambdas, doesn't tell us the V's. True? If we look at this matrix and this matrix, the characteristic polynomial is the same. Does it imply that the eigenspaces are the same? Yes? No? I do not know. Discuss. People, let me know. What would you say? People, what would you say? Yes, no, you don't know? No, no, very much no. Let's so that we are convinced that they are not. By the way, is it big enough as a tray? Is it thick enough? Okay. So, why do we have 3 and 2 that are my eigenvalues and eigenvectors? My eigenvalues, sorry. We need to have 3i minus a, this one that has determinant equal to 0, true. That means kernel of this stuff different from just the vector 0. Are we together on the definition of eigenvalue? An eigenvalue is something for which the kernel of the modified matrix is non-trivial matrix, trivial kernel. What does it mean? That once I have that I verify that this is true, I need to find V that belongs to this kernel. True? Let's compute it. Are we together on this? People? Perfect. If I compute this matrix here, A modified A, what do I get? Let's write it here. I'm going to get 3 identity minus A that is equal to 0, 0, 0, 1. True? This one, kernel of this one is going to be what? You tell me. Sorry, people, it's the USB. Find this kernel. Go. You need to find the kernel. You need to find all the vectors that are orthogonal to that stuff. People, look at me. The kernel of this matrix here is going to be all the vectors that are orthogonal to this and this. True? To be simultaneously orthogonal to both and both, I need to have something that is alpha 0. True? This one is going to be orthogonal to this because of course. And this one is going to be orthogonal to this because I need to have the second element equal to 0. Together? Indeed, this one is associated to this space here. You could see it immediately. but this is the way of computing. True? True? Are we together? Perfect. Eigenspace associated to -2 for this matrix here. Go. How do you do computations? We need to write kernel of lambda I minus a, true? That means kernel of -2, 0, 0, -2, minus 3, 0, 0, -2, true? We are going to get something that looks like, I think, -5, 0, 0, 0, true? Kernel of this stuff, 0 beta, true? Indeed, it's going to be associated here. How much are we together? For this matrix, we have eigenvalue, eigenvalue, eigenspace, eigenspace. Shall we compute the eigenspaces associated to this one? Let's do it. Let's compute the eigenspace associated to this eigenvalue here for this matrix. You go. Go, discuss and compute it. Pen and paper, people, the stuff here, you've got to be able to do it at the exam. So, people, I get, so if I take -2 identity minus a beta, I get this matrix here. And if I compute the kernel of this matrix here, I need to take 1 this one plus 5 this one. Are we together? This one, are we together that this is the kernel? Very much together, not at all, kind of. I do not see all the hands up. I really need all the hands up. This computation here is kind of trivial. If I see enough one that I think that we can go on. The computations shall be clear. Important thing is that this one that looks like this one is very different from this one. True? This is the kernel associated to this. This is the kernel associated to this. Are the two eigenspaces the same? No, they are different. You see? We have the same eigenvalues, but different eigenspaces. Together? That means that the trajectories are going to look like different. Are we together on this, people? So watch out. The eigenvalues by themselves do not say everything. We need to compute also the eigenspaces. Okay? They are in a certain sense the same. We will see it whenever we talk about diagonalizability. Even more interesting scenario. If I take this one, so are there questions about this, people? Ignore this one, it will be more clear. Actually, they are the same transformation. It will be more clear later on whenever we do diagonalization. The diagonalization. It's just a matter of scaling. But are there questions about what we have been discussing up to now?
Can you just show the eigen spaces of the second example drawing?
I think it was a -1 plus 5. That means -1 plus 5. That means this one. Other questions? No? Let's go to this example here. If I take this system here and I start with this initial condition, how is the trajectory going to look like? Going to do nothing, true? The free evolution is going to stay there, true? If I start here, how will the trajectory look like? Discuss. You should see from the matrix, because this point here is plus 1.5 plus 2.8, true? And then if I do 0, 1, 0, 0 times the stuff here, I get the x dot, true? That is going to be, the x dot is going to be equal to 2.80. That means that my x dot vector, how does it look like? It would look like something that is horizontal, true? That means that my x dot vector, whenever I put it on the x to get the trajectory, I get something that looks like this one, true? Which trajectory do I get? I get something that looks like this one. You see? Which system is this one from a physical perspective? Think at a practical example of a physical system that looks like, look, let me rewrite it. This one means position dot is equal velocity, velocity dot is equal to 0. True? True? Are we together that this one is actually this one? Are we together on this? Which physical system may you model in this way? Discuss. People, what would you say? Somebody here wants to suggest. A cylinder rolling without friction on a metal plate. True? You push it a little bit with a certain velocity and you will have it rolling, rolling, rolling. True? Are we together, people? 1, 2, 3. Excellent. So,
You said it straight away that the trajectory would be like horizontal like this, but to me, I would have like always before the eigenvalues, then the eigenspaces, the eigenvectors, then eigenspaces, and then I would have said that. How like because I'm not seeing with step speeds y. Is that a problem or?
I would say that this is a kind of domain expertise, in the sense that for a control engineer, a pure control engineer, the interpretability of matrices becomes, after a while, something that you see immediately. And this is a very special example that we are going to take over and over and over and over. Also because here we kind of see the solution here involves a t. Here we have p of t is equal to v0 times t, true? Plus p0, true? This one, is it an exponential? No, this is a very interesting object. This is a t e0t, true? If we think at a modal analysis point of view, in Laplace, this stuff here, what does it indicate? It indicates a double pole in the origin, true? Are we together on this part? Are we together on this part? How many zeros do we have here? 2. But at the same time, also here we have 2 zeros. But we don't have any t here in this system here. So this system here looks like it's only 1. True. We are going to dig down this. This is going to be the last part that we do, kind of difficult part of the course. Looks like the eigenvalues are the same. The spaces are different. Sometimes some t pop up. Sometimes the t's do not pop up. Why? When? We need to arrive at this, understanding this. Okay? Are we together that they are very different? Indeed. This point here, is it asymptotically stable, marginally stable, not convergent, convergent, not marginally stable, neither, you do not know. 1, 2, 3, 4, 5 for this one. Go, discuss. What would you say, people? What would you say? You would say that it's marginally stable but not convergent. Not convergent because if I start here, I'm not going to go back. And everything is an eigenspace, true? Everything is an eigenspace associated to 0. Okay? So we do not have convergence. But if I choose this epsilon for the marginal stability, which delta would you choose? The biggest delta that you would choose would be the same. True? Are we together on this? This point here, for this system here, how is it? Discuss. What would you say, people? Neither convergent nor marginally stable, because if I start, for example, here, I will escape. True? True? Very important. Very important. Look at this, people. Listen to me. This is an extremely important message. Same eigenvalues, completely different trajectories and stability properties. The eigenvalues by themselves do not give us everything. There's something missing in the picture. And it will be not only the eigenspaces, but also the generalized eigenspaces concept that we are going to reach soon. Are we together, people, on the fact that eigenvalues are not the unique thing that matters? Perfect. I think this one, the procedures, but I think we did it. We did it. Okay. No. Let's see if you see this one. Go. How do you see this one? So what would you say? Number 3, true? Because E1 goes in A1, E2 goes in A2, true? and this is like a 90 degrees rotation. All the visualizations that we did up to now, they are not valid. They are, whenever we get a rotation, it means that we have some complex eigenvalue. Okay? Together? Questions, people, on this part? Recommendation that I have, go through the slides, even if we didn't see all of them, because there are some numerical examples where you can handle a little bit better the computations that we did. Okay? Go through. Yeah?
For the question, when you say no real eigenvectors, you just mean that there is no real form.
The eigenvectors are not real. They're going to be like complex vectors.
Yeah. But we still have, they are still eigenvectors.
Yeah. It's a bad name. The real and imaginary part names are so misleading names that it's like the most unfortunate notation that got stuck in mathematics, because there's no more real stuff that an imaginary number. Anyway, so they are real in the sense that they exist. They are not real in the sense that they are complex stuff. Perfect. Thanks for the question. Okay.